Okay, so here with Tony Robertson, or Glen Tony Robertson, in your lab, in your working lab, at an undisclosed location. So, well, Tony, it is good to finally spend time with you. You did pioneering work with superconductors, with Podkletnov's work, and then Dr. Ning Li. You were working alongside them, and then you co-chaired the ISNPS STAFE conference, and then you ran the SPCIF conference after that. So you have been as deep into this area as anyone, and much deeper than most, for decades.
Yeah, to be clear, I started working with Ning Li before the NASA team, superconductor team formed, so I go way back into the late 90s with Ning Li. And to be clear, we never did do the impulse experiment, which is what we're trying to do here. We were trying to do the rotating experiment of a 11 or 12 inch superconductor disk, and we never tested that at all. But regardless of whatever the internet says, NASA never did do a test.
Yeah, if I remember right, you were saying, so, and this goes back a long time, but I remember talking to you years ago.
Back to about 1997 or 1998.
Yeah, well, okay, so let me go back to this. Is the history is starting to get cloudy now. So in the late 80s, I think it was 89, 90, right? Eugene Podletnov came forward and said that if you rotate a superconductor, it creates a column of reduced gravity.
90s. I think these papers only go back to, well, this was 2001, but I think the rotating experiment's only in the late 90s.
Okay.
Well, it could have been mid-90s to 90s.
And he talked about, if I remember right, because the superconductor, you have the steam coming off it, right, as the cryo fluid evaporates. And he said that formed a column above it, and he felt there was a reduced gravity area. And then he was, basically he was kind of running, I guess, up to floors above that and testing it. He said there were multiple floors, and he felt like there was a column of reduced gravity. And then that kicked off a bunch of interest here in the United States. And Dr. Ning Li and a couple of her associates, they got involved. They're here in Huntsville.
NASA, we had already formed the team at NASA, and then we heard about the Podletnov experiment, and Ning Li came to us with her own experiment, which I'm not going to get into it, but it was not really her experiment that she came with. But and then when we heard about the Podletnov experiment, we'd already went from me and just being me and her to being me and a whole team of people led by Ron Kozar, and we had David Nover on the team at the time. And so we decided to go look at the rotating experiment that Podletnov did, because it was only done at about 5,000 RPM, where Ning wanted to do about 50,000 RPM.
Okay.
There's a lot of difference in speed, so a different way to do things. And so we got on that bandwagon. So it really wasn't Ning Li's experiment that we were doing. It was the Podletnov experiment we were trying to do. And Ning Li was just a team member.
Yeah.
Under NASA.
Okay.
The team was not Ning Li's. It was the NASA team that Ning Li was part of.
And then her approach to it, she kind of relabeled it AC gravity, and then her thought was you could do positive or negative with the superconductor.
Right. She had her own theory. She had a paper, and then again, the paper itself has some questions about it, but I don't want to get into that either. But in the paper, there was, the way I understood it was that the paper said that if there's a factor that you put in these equations that's normally set to 0, and the paper suggested that if it wasn't 0, then you could see a gravity effect.
Okay.
And I don't know where she got the AC out of it, but during that time frame, she did do a lot of stuff on her own, promoting herself and what she was doing through UAH. So I can't say what she was thinking.
Yeah, she had a lot of irons in the fire. I remember that. Yeah.
So, but anyway, NASA never did do the experiment. We only made superconductors and try to determine if what we were making was correct. We never made one that we thought was correct. The money ran out, and we stopped.
Well, and so Podletnov, he had originally, I believe he claimed he was using like a 12-inch superconductor.
Yeah, somewhere around 11 or 12 inch. I remember correctly. I don't remember.
And so one of the challenges, if I remember right, one of the challenges was nothing that large has been made in the U.S. And I think there was a subcontractor that was involved to try and make that originally, right?
No, originally we were doing it in-house, and we tasked Ning Li. We would press them in at Marshall using a million-ton press, but we didn't need that much. But we used a million-ton press to press the big ones, and I even made 11 inches myself, you know. So, then we would give that press thing to Ning Li, who NASA had given her the money to buy the furnaces. They had them out at UAH, so she would fire them out at UAH, but she would never give them to us. You know, the concept was that we press the disc, she fires it the proper way it's supposed to be, and then give them back to Marshall to do a sample analysis of it, you know, cut it up and use our fancy equipment to see if it looks correctly inside. But she never would give us any of them.
Okay.
We never got any that she made at all. I saw a few of them, and most of the ones I saw had actually turned green, which is a different phase of the YBCO. And so we never got, so we got frustrated with her and started making them ourselves. So we made a few in-house ourselves. Most of them cracked.
Yeah.
And during the fire and everything. I even made one that was about a 1/4 inch thick, that was about 11.5 inches in diameter myself, that I fired. And it didn't crack until after I cooled it. And then when it was warming back up, it cracked.
Well, that was one of the surprising things for me, right? It's the engineering challenges that you don't think about when you're reading about it, you know, in the news. But so yeah, the cracking, especially with the larger sizes. Another one was, if I remember right, these tend to disintegrate when you're spinning them up, right? And
yeah, we were gonna put, you know, like a Kevlar ring around it or something like that, or some kind of plexiglass ring to keep it from coming apart. But we never got that far.
Yeah.
That far. And but yeah, the superconductor also deteriorates from moisture.
Okay.
So when you're cooling it down at room atmospheric pressure, and when it starts warming back up, moisture condenses on it, and that moisture can deteriorate the superconductor and completely break them down. In fact, I used to make them, and then the way I would rather than spending the time grinding them, I'd throw them in a bucket of water and let the water disintegrate them, and then pour the water off and let it dry out. That's the way I reused the powders.
Well, then there was also another thing that I remember, and I think this was one of the areas you were getting into, was so there's a glaze that forms on the outside of it, and so the structure isn't completely homogeneous, right? You've got a different crystal structure inside of the superconductor.
You melt texture it. They call it top seed melt texturing. You put a little seed of a superconductor material that's not YBCO, but be like cesium BCO,
okay.
or something other element you put in there that wouldn't melt at the same temperature that the YBCO was. And you put them on top. You take it up to, I think I was actually looking at around almost 1100 C, and let it sit there for like, I don't know, I forget what it was, almost like 3 days. And then you bring it down slowly, about 1 C an hour for about 100 hours or so. And so from those seeds, it would form a crystal structure that was basically an 8-sided crystal through the sample itself. So that crystalline structure would then kind of map the superconductor through the superconductor through this crystal layer and grow through the samples.
Okay. So
I made some small ones that looked pretty good, but the crystals were, you know, maybe the size of a pencil head in it. But Oak Ridge sent us one that had crystals in it that were probably 1 inch in diameter. Real big crystals, real pretty thing. And moisture killed it. It just broke all to pieces after using it a while.
yeah, so that I mean, and the only reason I mention all this is you know, again, when you read about it in the news, it's like, okay, superconductor, spinning, gravity, it should be a pretty simple test, but there's a lot that goes into it, especially in terms of chemistry, materials engineering, you know, and then you've got the mechanical stresses, and like, and again, I think you told me this years ago, NASA only got it up to, I think, a couple of hundred RPM or something.
Well, NASA never spun one. We got a Ron Kozar got an SBIR through a company I think out of Illinois, it could have been Indiana, but somewhere up north, who kind of redid what we did, and they got to the point where they levitated one in a cryostat. It was never rotated either. So no rotation was ever done between NASA or the SBIR.
Okay.
We never rotated anything.
Now, did Ning Li, do you know if she rotated them or?
No.
Okay, so really the Podletnov experiment was never really replicated here in the U.S.
It was never done. The rotating was never done by NASA, but if you read the internet, it says it did.
Yeah.
So never did it. Never did the test. We only did some preliminary work to make the superconductor, both at NASA and through the SBIR. That's all we did. The only difference between what we did at NASA and what the SBIR did is they made a levitation system in a cryo tank that showed that they could levitate what they made. We never even did that with the big one. We never levitated.
Okay, so we should put a pin in that one. NASA never completed a replication of the Podletnov rotating superconductor. And that's not to be negative against NASA. It's just pretty darn complicated and hard to build.
The team structure fell apart on the NASA side. That's what, between even the NASA people and Ning Li, it got to the point where everybody was going in different directions. Then we ran out of money, so.
Yeah. Lots and lots of stuff going on.
I've got a small sample that's melt texture.
Yeah, do you want to show me?
Yeah. If I can find it quickly. If you notice all these ones that are broken up, that used to be big pieces at one time. Let's see. This is what you would call melt textured seed, top seed row. And if you can see it reflecting, you can see the crystalline structures trying to form around the seeds. You need the light reflecting off of it to see those crystals.
Okay, so that's the melt texture. So they put, again, it's a small kernel of other superconductor on top of the YBCO.
Yeah, and you take, like I said, it takes about a week to make this because you're sitting at about 100 hours at.
Yeah, so this is kind of like pottery, and I remember reading about the process for this. And so you put it into the kiln, and you have to leave it there for a period of time, and you have to take the temperature up and then bring it back down slowly, if I remember right.
Yeah, to just center it where you can test it for superconductivity is not very long. This is centered.
Okay, let me go back in there and see if this. There we go. That looks like it's about 6 inches in diameter.
Yeah, I've lost the 6-inch die.
So you press these to get them into the right shape, and then you center them.
But we might be able to crush this down and reuse the material.
Yeah, and it looks like there are a lot of experiments in there.
That's a mini rotating disc.
Oh.
And we were trying to make one like this that was 11 or 12 inches in diameter. So this was actually made for a different project, but. The specimens all got destroyed due to moisture over time.
So you're working on new experiments.
This is not a new experiment. We're trying to replicate the ones that are described in these two papers. These two papers are basically talk about the same experiment, except this is the non-published version, this is the published version.
Okay. Let me see if I can lock onto that with my. And then I'll go over here to this one too.
I put that we can go find that if we want to. That address. There is a little difference in some of what they're talking about in the papers, so you have to pay attention to both papers. The larger one tells you actually more detail how to make the superconductor than the smaller paper does. But basically what it's talking about in this is putting a 4-inch superconductor on basically on a cryo head, so you can cool the superconductor down. It's in a vacuum chamber, and the way they talk about it is they take it down to about 10 millitorr, which basically is a good brand new roughing top that gets you 10 millitorr. And then he says that it cryo cools down to about 7.2 millitorr, which I assume that's when they cooled the superconductor down. And the superconductor starts acting like a cryo pump and pulling it up. And what he talks about in the paper that's really interesting is that he said when they initiate the discharge, a white cloud forms over the top of the superconductor and then moves as a single body, hitting the grounding plane hard enough that it makes an impression the size of that cloud, which I assume is around 4 inches in diameter. And to do that cloud had to be in a Bose-condensate state. It had to act like it was a solid piece of material hitting that grounding state.
Yeah, that is interesting.
And if that's true, that's the largest sample of a condensate that's ever been produced in the world.
Well, and that reminds me of, let me see. Excuse me, and this is not his, so he had the force beam generator too.
That's what that is.
Oh, okay, yeah, I know, okay.
What I'm talking about here is this is the impulse experiment. We learned about the impulse experiment after we brought Podletnov over to talk to him, came to NASA, and he said, by the way, we're doing this other experiment where we're impulsing. And then shortly after that, the papers came out and stuff. So he told us kind of, I don't know about first, but he told us about it.
Yeah, and so, and again, just for, whoever watches this, so Podletnov had 2 different experiments, and people get really confused about that.
The rotating larger disk was done in Finland. The impulse experiment, from what he said, was done in the basement of a university building in Moscow.
Yeah.
And the test we're trying to do here is the impulse experiment, not the rotating one. After we found out about the impulse experiment, I basically told him, he said, that's a better test. It might be easier than even rotating test. But at the time, Marksbanks weren't that available. In fact, we contacted a company that wanted like $200,000 for a Marksbank that you can basically buy now for like a few $100s. And that's what we got here. This is part of a Marksbank that we'll mount up.
Okay, so it's going to go up there.
Yeah.
So you're basically doing a high voltage, high energy pulse. And if I remember right, for him, he talked about something up to 500,000 volts, right?
Yeah. This is about a 600,000 volt stage, and this will give you about another 300,000 volts. And we're going to put them together, but that's at full voltage, and we don't want to overstress the cap, so we'll probably less than that. But we still probably can get close to 700 to 800,000 volts out of this system.
Yeah.
The problem is that the paper doesn't discuss the joule rating of the Marksbank that he uses.
Okay.
So the joule rating on this might be too small. So we've got plans to build a bigger one so we can get a higher joule rating. Because I did a paper where if you look at the layering in the superconductor and assume there are capacitors, the joule at 500,000 volts, the joule rating would be like 2 orders of magnitude higher than what this will give. So we don't know if this will give us a proper impulse. So we'll have to keep scaling the Marksbank up until we see something corrected.
And he had talked about, if I remember right, warping thick pieces of metal with it.
Yeah, 150 meters.
And crushing brick.
He was probably up around 200 megavolts when he was doing that.
Yeah. So if this was a gravitational wave, I mean, I mean, there are incredible potential for this.
That's the reason why we're going to point it towards the ground. So if we get seismograph people showing up, we know we did something. But if you want to stand here and look at this thing.
Okay, so then.
What we're building is we'll have a cryo chamber in here. The bottom will be in the vacuum chamber, in this glass vacuum chamber. There'll be clamshell between here with cryo epoxy, so that we won't have any vacuum leaks in here. We'll also tap the high voltage to the chamber, so that it becomes our high voltage electrode too. So when we pour liquid nitrogen in, we'll cool the superconductor down. We'll have to do some profiling tests with the superconductor with some thermocouples, so we can get a gauge on how long it takes it to cool down, because we don't want the thermocouples in there during the high voltage test, or we can destroy instruments or hard places that doesn't want it. So after we profile the temperature on the superconductor, we take the electrodes out and dump it down. Then what's not in the paper is that we don't know what the discharge distance is. So we'll have to play around with the distance between the superconductor and the grounding plate to determine how far it has to be apart. And 500 kilovolts in the atmosphere is about 19 inches. But in a vacuum, we don't know. I mean, it should be longer, but be actually in a vacuum. So we don't know. So we have to get it closer for it to actually discharge. We don't know what that distance is. If you go by the drawings in the paper and assume that the chamber's around 1 foot and everything's to scale, then we can get an approximation of what we think the distance is, but it may not be right. We'll have to figure it out ourselves. And then we have a chamber here that actually was part of a NASA test that Tim Pickens had bought that we're using in the grounding plane. And so basically it'll shoot into toward the ground off of the Marks bank down here, and we'll be able to.
So in this setup, so you've got the Marks bank on the right.
The Marks bank will come up.
It's going to go over the top, down through the chamber, and down into the ground.
And then the grounding, we're going to put we have an electrode that we're going to put in one side. This side will actually be rotated around here, and we'll drill a hole in this, and we'll bring the ground down through here.
So if this works, this may actually, in theory, this can actually crush the concrete underneath it.
We're not going to test it here.
Okay.
We're going to do all the preliminary tests here, and then when we do the gravity test, we're going to go out in the middle of a field somewhere.
So the other thing that Podletnov talked about, he wasn't as forthright about this, but he'd said that there were strange effects behind the superconductor.
Yeah, I asked him when he came over. He says, "What did you see anything about the other direction?"
Yeah.
His response was, that, "Yeah, if you stand there, you'll burn your skin."
That's what he told me. Yeah.
And so my assumption is that it's putting a gravity wave out one way and an EM beam out the other way.
Okay.
So that's the reason you're getting burned, because there's very high microwave energy coming out the other side.
That would make sense.
That's another reason why it's up this way, because we don't want to destroy people's equipment, but in one direction and kill people in the other.
So with the blue chamber, then, is there anything unique about that? That's a vacuum chamber?
Yeah, Tim Pickens found this, and that's part of it too. It was some kind of balloon experiment that had a helium chamber in it. It had an interferometer built inside, and they were looking for something up in the atmosphere. So Tim said, "It looks pretty, let's use it." So we're using this part of it. We've got the rest of it over here, but I don't really need it. So this is going to be our ground. This helps protect it. The hole that's built into the plate at the top of here comes out to here, so it's a lot bigger than that hole. But the grounding plane will actually be real close to the hole to start with, and we'll move it downward. And if we have to go down really far, then we might put a plexiglass tube to help protect it from trying to go sideways. And if we have to go real far, we'll put the other piece on it and
Yeah.
bigger chamber.
So you mentioned Tim Pickens. I guess one thing I should ask about is you're putting together a team, right? This is the coalition of the willing to.
Tim contacted me and said, I really would like to do that superconductor experiment. I said, well, let's do it. I've been wanting to do it anyway. I had bought another chamber that's in the other room in there to do that experiment, but I never went after it because of the fact that, like I said earlier with the Marchbanks, they wanted like $200,000 for a Marchbank back in the day.
Yeah.
And then I found out, hell, everybody in their brain is making one nowadays. And so so they're not that hard to make. It's still not cheap. It's about $10 a piece, and there's 30 in here. So, and I don't know how much the resistors are.
So in terms of this system, you talked about trying to do some testing maybe later this year, right? So towards the end of 2025?
No, I probably won't be doing any testing until next year.
Okay.
Because I'm going to be busy all summer. So basically, I'm through with this. When I'm not busy, I may do some more stuff, but we still need some more parts. I just ordered the flange that we need to adapt to this for that. But Tim's already tested this, and so we know it's working.
Well, I'll tell you, I'm super excited that you're getting back into this, especially putting together, a team to work on this. I mean, Ning Li, there were lots of conspiracy theories, but the takeaway, like Paul Muir had kept in touch with her, and her son is still out there. She got sick and she passed. That's, and
From what I heard was that after we ran out of money with NASA, she got about $400,000 from the Army and was doing something. What she was doing, I just know she was still doing superconducting stuff. But what I heard was she was doping it with some stuff that she should have been wearing a full mask suit and stuff. It was pretty, and so she got sick from that.
okay.
And then she got breast cancer.
Yeah.
And she went back to China for a while to do the Chinese med for breast cancer, and she came back. And then after she came back, I actually met her and talked to her about it. But I don't believe she ever did anything after she came back with the superconductor.
Yeah, that was kind of my takeaway is that it just kind of stalled out, right? I mean, and again, it's one of those things. I mean, there's so many ideas that kind of come and go, right? And the media spotlight kind of moved on.
One of the problems that actually killed anybody other funding it was because the internet started saying that NASA completed the test and didn't see anything. So nobody wanted to put no more money into it. But we never completed the test. We never did the test.
Yeah.
And so everybody who has ever claimed to do the test that I've read their paper never did the test to the degree that these papers talk about. They would either have too low a voltage, too small a superconductor, not a two-layer superconductor. There's always something not right in all of the experiments. In fact, most of them were done with like 2-inch discs or smaller. And Hadley did said he had a 4-inch, but it was just 2-layer. I mean, it wasn't 2-layer. It wasn't 2-layer. And I don't believe that he went up to the high enough voltage. I'd be wrong about that, but I don't. But he was the closest person to doing the test, but it still wasn't the test described in the paper.
Well, and then I've kept up with Podletnov. It's been a couple of years, but he basically went back into more traditional work in Russia, and it was the same issue, right? He just couldn't sustain the funding, and so there were lots of conspiracy theories about the Russian government, doing this, that, and the other thing. But from what he had told me, basically, it just, the media spotlight moved on, and the funding ran out over time, and he's like everybody else. He has to earn a living. So
Podletnov actually claimed that he was able to see a gravity effect from a non-superconducting material too. I forget what he said it was, but he did claim to have done some other experiments with non-superconductors that saw a similar effect.
Yeah, so one of the things, and I started exploring this a little bit more earlier in the year, and I'm sure you're aware of this too, right? Russia has this independent scientific community. They don't communicate with the U.S. that well. And Podletnov was working with 2 or 3 other people over there. And part of it's the language barrier, right? But then part of it is just poor communication. And I kept thinking, if we were able to communicate more effectively between these two cultures, maybe we could solve these issues together. So
yeah, I could be wrong, but Podletnov especially the rotating experiment, did not know his own experiment. And at least that's the way my impression was. From what I gathered was that the large superconductor that he was using was borrowed. He didn't make it. It was borrowed. And from looking at the experiment and what they were doing to the superconductor, my impression was that what they were trying to really do with the rotating experiment was to see if they could use a superconducting material as a radar type shield, what they really were doing.
Okay.
And how they found out that there was some type of gravity effect going on was that the Podletnov sponsor at Finland University he was at was a pipe smoker who came into the room.
That's right, it was pipe smoke.
One day, and the pipe smoke went over the experiment and started rising above the experiment. And since it was in a closed chamber, that even though it was sugar was being cooled, the chamber wasn't really getting cold. So they ruled out cryo effects and said, something else is going on. So then they went and put a test mast above it and saw that it lost weight.
Yeah. Yes, it's been a while, starting to fade out. I was thinking it was steam off the nitrogen, but it wasn't. It was pipe smoke. I remember.
Pipe smoke, we actually talked to the daughter of his sponsor who had died by then, the time we talked to her, and she told us the big stories.
Well, and then Podletnov actually flew out here to help NASA, right, for a while.
He flew out here and talked with us for a day or two. And so we just grilled him with questions and stuff. He never really helped us here. We were paid. Under the SBIR that Ron Kozer got in place, they were paying Podletnov to be an advisor. So they paid Podletnov a lot of money under the SBIR to advise. But from what I've been told and gathering, that a lot of the money that they spent in the SBR went to pay Podletnov and to make superconductors. Podletnov suggested, like he was learning how to make the superconductor. In other words, it wasn't just, you make it this way. He said, let's try this, let's try that, let's try this. So Podletnov didn't understand the superconductor. I'm sorry, but that's the impression that I have, is he didn't understand.
Well, so we're going on 30 years now with these superconductor experiments. I mean, you're still working on it, so you obviously think there's something there, right? So
the experiment really needs to be repeated to the degree that the papers talk about. Until you can actually do that, it's all speculation. And there are holes in the paper. Like I said, it doesn't tell you what the joule or energy rating is of the Mark bank that he uses. We don't know that. We don't know what the discharge distance is that he actually used in his experiment. So there are some uncertainties that we'll have to learn ourselves what we're going about, because the paper doesn't tell us exactly what they are. He does have a good detail of how to make the superconductor here, but all that material about making superconductors in these papers is what he learned through the NASA SBR.
Okay.
And so we can't really guarantee that's true either, because if he was just trying to learn how to make superconductor, who made the superconductor and how really was it made? So the superconductor itself is an uncertainty.
Yeah, although I think one of the advantages, and we were talking about this on the drive over, one of the advantages now to having all this time in there is a lot of time to analyze what could be potentially going on, a lot of new physics. You talked about a lot of complex, basically energy transfer inside of the superconductor, right?
Yeah, I wrote a paper that's in the gravity book that I edited with Modenese. I think it's chapter 4, and that describes how you can get an energy wave out of a superconductor.
Okay.
And so I went into some great detail on some of the superconductor effects that could be involved in this. So that's a great reference, even if part of it's not true. It is a great reference to all the things that could lead up to a gravity wave coming from a superconductor. I even used the gravity wave equation out of Wheeler, Meissner, and Thorne book, big thick book. So the force I came up with matched what Podletnov claimed he saw. So whether it's just whether I was making the fit or not. It did come out. I didn't try to make it fit. It did come out to be that.
Okay.
But knowing what the results are kind of affect what you do. So I can't say that it's 100% true. But it's in that paper that shows that you can get a gravity wave out here if you can move these. Move a number of these Cooper pairs fast enough, then you can get you can just from that motion get a gravity wave created. Since then, I've got another model I've been working on that kind of suggests that this might be something different, which I'm hoping this test will help me prove my model too. But my model doesn't rely on the gravity wave equation; it's a different set of equations. So I'm going to try to correlate my stuff to this if we see something. If we don't see something, I can't do that. But
yeah. Well, and then there's also this big maybe, right? But superconductors, because they are hard to work with, if we can figure out what could be potentially going on inside of those, maybe we could apply that to, like, again, we were talking about 2D materials and lots of other, novel things that have been developed over the last few years, right?
Yeah. If you can understand what causes gravity, then you can then make things that maybe don't need the cryo system.
Yeah.
So the cryo system is a big no-no when you're trying to do something in space. It's because you would basically have to turn your whole craft into a cryo chamber. And that's almost an impossibility for really in space. I believe we will eventually go to space. But we can't go to space using the current technology.
Well, Tony, thank you so much. Thank you so much. It's truly an honor to be able to see your lab and see everything you're working on.